All right, calculus students, let's take a look at the second half of our notes on locating extrema. So in the first video, we attempted to locate the extrema graphically using our TI graphing calculators or Casios or even Desmos. And now we want to talk about the problem-solving strategy for locating the extrema on an equation. So remember from the examples above, the absolute extrema can be located on the endpoints. So when we start every problem, step one is going to be to evaluate the endpoints of the function. Then we want to find the critical points that lie over the interval, because we know if a function has an absolute maximum or minimum, that point is guaranteed to be a critical point. Now when we find the critical points, they're not always maximums and minimums, they're just potential candidates. Finally, once we've calculated the two endpoints and calculated any critical values between them, we want to compare all three values. The largest value was our absolute maximum, and the smallest value is our absolute minimum. So let's get started on example 1 by finding the value of f at each of the endpoints 1 and 3. We need f of 1, there we go, equals -1 squared plus 3 times 1 minus 2, which is equal to 0. Then we're going to evaluate f of 3. Please use a calculator. We've got -3 squared plus 3 times 3 minus 2, which gives us -2. So what we're looking at now, since -2 is smaller than 0, we have a candidate for an absolute minimum here with -2. We have a candidate for an absolute maximum with 0. What we need to check is if the critical value is either greater than 0 or less than -2. So to find the critical point, we know critical points occur when f prime of x equals 0. So we're going to find the derivative of our function. And then we're going to set that derivative equal to 0. I'd rather add 2x. I'm just changing my mind here. Add 2x, and x equals 1.5. Now evaluate f of 1.5. Again, use a calculator to make sure that you're not doing anything silly with your calculations. All right, I'm getting 0.25. Since 0.25 is the largest of these three values, we're going to dub it our absolute maximum. -2 is the smallest of our values, so we're going to call it our absolute minimum. And that's the algebraic approach to locating absolute extrema. Taking a look at the second example, now's a good time to pause the video, try the example on your own, and then play the video back to make sure that you did it in a similar fashion or at least receive the same answer. So the first thing we want to do is take f of 0, which is 0 in this case since both terms have an x, and f of 2, which is 2 squared minus 3 times 2 to the 2/3. Go ahead and type this in a calculator and get a decimal approximation. When we're looking for absolute max and min, we do want to be able to compare the values. So it's not as essential to know the exact value. It's more essential to know if it's larger or smaller than the other options. So right now we have a candidate for absolute maximum and a candidate for absolute minimum. Take the derivative of the function. When you reduce 2/3 by 1, you're left with an exponent of -1/3. you can simplify the coefficient of 3 with the 2/3, and that gives us f prime of x is equal to 2x minus 2 over x to the 1/3. We're going to set this function equal to 0. And then when you're dealing with solving a rational function, one of the top strategy choices is to multiply throughout by a common denominator. Since x to the 1/3 is the only denominator in this problem, we're going to multiply each term by x to the 1/3. That gives us, and I'll go ahead and write that out, times x to the 1/3 here, which gives us 0, times x to the 1/3 here, which we're going to need to simplify, and times x to the 1/3 here, which is going to eliminate our denominator, and that's the purpose of the multiplying by a common denominator strategy. Okay, we've got an equation that's now is not rational anymore, but it does have two x's in a single term. So in order to solve this by isolating the variable, we're going to want to combine those factors, that x times x to the 1/3, into a single value of x. So remember that the exponent here is actually 1, and we can get a common denominator and add these fractional exponents by following the product rule, which states if the bases are the same, add the exponents. So what is 1 plus 1/3? We're now getting an exponent of 4/3, and we can solve this equation for x using 3 steps. Add 2 to both sides, divide by 2, and then raise both sides to the reciprocal of your rational power. If you're looking to eliminate an exponent, you just want to raise it to its reciprocal, because 4/3 times 3/4 is to the first power, and raising something to the first power is an identity. What is 1 to the 3/4 power? It's 1. So we know our third potential for an absolute extrema is our critical value, f of 1. Plug in 1, and you're going to get 1 squared minus 3 times 1, or negative 2. That means 0 is our absolute max, and I'm just going to use the same colors so I don't have to write the words again, and I don't think that's the same color. Negative 2 becomes our absolute min. At the bottom of the notes, you're going to see 2 theorems that I need you to familiarize yourself with. The book does a pretty good job of explaining these in a little bit more detail. I'm just putting the wording so that you know. Extreme value theorem. This is the theorem that lets me know the functions above over the bounded intervals had to have an absolute max and an absolute min. Otherwise, we wouldn't be looking for both. If f is a continuous function over the closed bounded interval from a to b, then there's a point in a to b at which f has an absolute maximum and a point where it has an absolute minimum. It's got to have both because it's been bounded. The function can't go to infinity when it's on a limited closed interval. Now, Fermat's theorem, when we talked about critical values. It basically says if you have a local extrema, either a max or a min, and the function is differentiable, then the derivative is guaranteed to be 0. Which is why when we're looking for our extrema, we are finding the derivative and setting it equal to 0. This concludes the notes for locating extrema, both graphically and algebraically. So thank you for watching.